Welcome to Daily Papers, the podcast where we break down the latest research papers into something you can actually understand. Today, we're diving into a paper that sounds a little intimidating, but has some really cool ideas about how to make AI smarter. It's called LLMs Can Learn to Reason via Off-Policy RL.
Right, so let's break that title down. LLMs are large language models, like the AI you might chat with online, and reason is exactly what it sounds like. We want these AIs to be able to solve complex problems like advanced math or writing computer code, not just predict the next word in a sentence.
Exactly. And the second half of that title, Off-Policy RL, is where the magic of this paper happens. RL stands for reinforcement learning. You can think of it like training a puppy. You tell it to sit, and if it sits, you give it a treat. If it doesn't, no treat.
The AI gets a digital treat or a reward every time it solves a math problem correctly. It learns over time that correct answers lead to rewards, so it tries to get more answers right. This is how we push LLMs to develop these reasoning skills.
But there's a huge hidden problem in how we do this. The most popular training methods assume that the AI is learning in a very specific, orderly way. They are what we call on policy.
Let's use an analogy. Imagine you're a single chef trying to perfect a new recipe. This is on policy. You cook the dish based on your current recipe, you taste it, and you immediately update your recipe based on that one dish. You are learning directly from your own most recent actions. The student and the doer are the same person at the same time.
The problem is, that's not how we train giant AI models. It's not one chef in a quiet kitchen. It's more like a massive, chaotic restaurant kitchen during the dinner rush. You have one head chef, let's call it the trainer, who is trying to improve the master recipe.
But then you have hundreds of line cooks, let's call them line inference engines, who are actually cooking the dishes. These cooks are all working at lightning speed, but they might be using a version of the recipe that's a few minutes or even a few hours out of date.
So the head chef, the trainer, is getting feedback on dishes that were made with an old recipe. It's trying to learn and update its master recipe based on slightly stale data. This is what we call off-policy learning. The AI is learning from the actions of a past version of itself.
And this mismatch can cause all sorts of problems. The training can become unstable, or the AI can just completely fail to learn, a problem researchers call policy collapse. It's like the head chef getting so confused by the feedback that they just start writing nonsense in the recipe book.
For a long time, the standard approach was to try and fight this. The most popular method, called GRPO, uses complex math to try and correct for the stale data. It's like the head chef trying to calculate what a dish would have tasted like if it had been cooked with the brand new recipe instead of the old one.
As you can imagine, that's really hard to do and can be very unreliable. So the researchers behind this paper asked a different question. What if, instead of fighting the chaos, we embrace it? What if we designed an algorithm from the ground up that is built for this messy, off-policy world?
And that's what they did. They created a new algorithm called OAPL, which stands for Optimal Advantage-Based Policy Optimization with Lagged Inference Policy.
A bit of a mouthful, but the core idea is really elegant. OAPL tells the AI trainer to do two things. First, and most obviously, try to get the highest reward possible. Solve those math problems, write that code.
But there's a second crucial goal. It also tells the trainer, don't get too different from the line cooks who are generating your examples. It puts a kind of leash on the trainer, preventing it from running off in a completely new direction while the inference engines are still using an old recipe. It keeps them loosely in sync.
It doesn't force them to be identical at all times. Instead, it lets the trainer learn for a while on its own, and then every so often, say every 50 updates, it stops and syncs up the trainer and all the inference engines to the new master recipe. Then the process repeats.
So the big question is, does it work? And the answer is a resounding yes. They tested OAPL against the standard method, GRPO, on a series of difficult competition math benchmarks. The results are pretty clear in the paper's charts. OAPL consistently scored higher than GRPO.
And not only did it perform better, it learned more stably. The authors looked at a metric called entropy, which you can think of as the AI's creativity or its willingness to explore different answers. With the old GRPO method, the entropy just collapses over time. The AI gets stuck in a rut, giving the same kinds of answers over and over, even if they're wrong.
But with OAPL, the entropy stays high. The AI keeps exploring, it keeps trying different paths to a solution. This ability to explore is likely a key reason why it ends up with better final performance. It doesn't get stuck.
The results on code generation are even more impressive. They compared their OAPL-trained model to a powerful coding model called DeepCoder. OAPL was able to match or even slightly beat DeepCoder's performance, but, and this is the amazing part, it did so using only 1/3 of the training data.
That's a massive improvement in efficiency. It means you could potentially train these incredibly powerful models faster and with less computational cost. They also tested its limits. They found that OAPL could still learn effectively even when the inference engines were 400 updates behind the trainer. That's a huge lag, far more than previous methods could handle.
It basically proves that their embrace the chaos philosophy works. You don't need the trainer and the data generators to be perfectly in sync. By designing an algorithm that understands and works with this lag, you get a system that is more robust, more efficient, and ultimately produces a smarter AI.
So what this paper shows is that sometimes the most elegant solution isn't trying to force reality to fit your perfect theoretical model. The reality of training LLMs is messy and asynchronous. By building a tool, OAPL, that thrives in that messy reality, these researchers have made the whole process better.
A great example of meeting the problem where it is, not where you wish it would be. That's all the time we have for today. Thanks for tuning in to Daily Papers.